Okay, so today we'll have a look at polynomial rings. Okay, can anyone tell me what do you expect to define a polynomial as? What is a polynomial over a ring? So we have defined the ring of formal power series over a ring R, right? We have defined the ring of formal power series over the ring R. Okay, what do you expect to define a polynomial as? In terms of the formal power series, what do you expect a polynomial to be? What does a polynomial look to you like? Yeah. Yeah. So you don't want those infinite number of terms. You want only finitely many terms. In other words, you want eventually you want all terms to be 0. Right? So there should be some k, which we generally call as the degree, such that after that k, so maybe at that k it's non-zero, and after that k it is 0. So that's what the polynomial will be, right? It will be just basically the set of all those elements such that after some stage they are 0. Okay, so that's what we are going to define it as. So let us show that this kind of a set, the set of all these collections, is actually a subring of the ring of formal power series over R. Okay, so let's see. So let R be a ring. Let R be a ring, and as you see, this is what I kept this notation for. We'll take this Rx is the set of all these formal power series, that is summation an x raised to n. I will stop writing n going from 0 to infinity in most cases, okay, because it is time consuming. Okay, so elements of the ring of formal power series over R such that, okay, after some stage all these terms are 0. Okay, so such that there exists some k in n union 0 such that for every n greater than or equal to k or strictly greater than k, yeah, that's fine, ak or an is equal to 0. Okay, so an element a formal power a formal power series, okay, is in this set if after some stage everything is 0. Is that okay? So that's the formal, that's the polynomial ring. Okay, so prove that Rx is a subring of R. Okay, so how do I prove that this is a subring? Yeah, how do I prove this is a subring? What do I need to show to prove that it's a subring? Closed under subtraction and multiplication. These are the two things that I need to show, that it's closed under subtraction and multiplication. So I'm going to fix to a certain type of notation in this chapter purposely, just to make it a little easy. So when I write capital A, when I denote the formal power series by capital A, I will use the coefficients small n, small an. If I use capital B, I will use the coefficients as small bn, just for convenience. Okay, so we'll take ax to be this an, and we'll take bx to be bn in Rx. That means for both of them, after some stage, all terms are 0. So there will be a k such that after some stage this is 0, and there'll be another element such that after some stage this is all 0. Okay, and I will stick to using T and S. Okay, so the first observation you can easily make is that if either a of x is 0, okay, I will denote that by 0x, just notation. That is I hope everyone can see that 0x is going to be an element of this. 0x is basically the formal power series such that every term is 0. Okay, again we think of formal power series as a sequence, right? By this thing, they are actually, it's a sequence. Okay, as I have said, this x raised to n is just like a placeholder. Okay, so it's just like a sequence. So all these an's would be 0. If all an's are 0, obviously it falls in that. Right? That's your identity element in this ring, right? So we know that it is this thing. So if this is 0 or this is 0, then I hope everyone can prove that ax minus bx will have to be in okay, I believe that you can prove this. This is not too difficult to see, because if bx is 0, then ax minus bx is ax itself, and ax is in this, so it will fall there. If ax is 0, then minus bx, right? If after some stage all the terms of bx are 0, then if after some stage all the bn's are 0, then obviously also after some stage all minus bn's are 0. So that will mean that minus bx is also in this. So I will keep that case out. So if this is 0x, then this is in this. Okay, so I hope you can do that. If you don't, so hence we will assume that they are both non-zero. Hence we assume that a of x is not the 0 and b of x is also not the 0 formal series. Now, when they are not the 0 formal series, okay, in fact, I am doing a little extra work here, but it's on purpose to get something more than what the proof is, more than what the exercise is asking, as we will see later. So, when this is non-zero, it means that there is at least one element here which is non-zero, right? So that means, but we also know that this is in Rx, A and B are in Rx, right? So that means there's going to be some maximum maximum subscript for which this is non-zero, right? So that I'm going to call as T and S. So let T be the maximum of n in n union 0 such that an is non-zero. Okay, what do we call this T generally? To the polynomial ax, what is this T called? I've taken the biggest n for which an is non-zero. What do we call that? The degree of the polynomial. That's right. And we will take this s, which we will define later, okay, the degree. But keep in mind that essentially this T and S are basically going to be the degrees of the polynomials. Okay, this is the set of all, this is the maximum of the set of all n in this, such that Bn is non-zero. Okay, now I'm looking at Ax minus Bx. I want to say that Ax minus Bx is 0 after some stage. Can you tell me some stage after which it's definitely going to be 0? I don't even need to catch hold of the degree. Can you give me some stage after which it's all 0? Yeah? Sum of both of them is actually right, but you're going up too much. Earlier than that it might take place. sum will actually work, t plus s you're saying, right? It will actually work, but it actually happens before that, before the sum. No, not difference. Difference could be anything. Think about it. You have two polynomials and you subtract it. When you take two polynomials and you subtract, what do you expect the degree to be? The maximum of the degrees of these two, right? So that's what we are going to take it to be. That's exactly what it is. So that's the one. Okay, so for so if you look at any n greater than the maximum of t and s, what will happen? For n greater than the maximum of t and s, an and bn are both 0, right? Because if n is greater than the maximum of t and s, it is greater than t and it's greater than s. So therefore this will tell us that an will be 0 and bn would be 0, right? Which would imply that what does this imply? That an minus bn is 0. So what have I proved? That when n is greater than the maximum of t and s, an minus bn is 0. But this is nothing but the coefficients of a of x minus b of x. That's the way which we have defined a of x minus b of x. So therefore, this tells us that, I hope this is okay, a of x minus b of x. What is this polynomial? What is this formal power series? We don't know, it's a polynomial yet. This is an minus bn. See, you can see this satisfies the property that after some stage all terms are 0, right? After some stage all terms are 0. So therefore it falls in the set Rx. It's natural to believe this, right? When we work with polynomials, we subtract polynomials, we get polynomials only, right? If you divide a polynomial, you might not get a polynomial, right? You all know example, at least when you work in fields which you all are familiar with in analysis, like R, if you take 1 minus x and divide it, 1 upon 1 minus x, what do you get? Anyway, let's not think about that. So this is a minus b. Next we need to check that this is closed under multiplication, right? That this is closed under multiplication. We don't know it is closed under division. It will not be closed under division. Not it will not, but at least in Rx, where R is the real field, it is not going to be closed under division. But otherwise, what we can use, let me see then. Yeah. So can anyone now tell me what do you expect? What should I take here to prove what is going to be the coefficients of Ax into B of x? What is the Cn? Summation. Okay, I you want? I going from 0 to n, ai, bn minus I, right? After what stage can you say that the Cn's are 0? Again, you want intuition, work with the polynomials that you have. If I have a polynomial and another polynomial and multiply it, what will its degree be? The sum of the degrees of the two polynomials, right? If you have a polynomial of degree 3 and multiplied polynomial of degree 4, then the resultant polynomial generally is going to be a polynomial of degree 7, right? Because the third power of x you multiply to the fourth power of x in the other polynomial, you get degree 7, right? X raised to 3 into x raised to 4 is x raised to 7. So that's exactly what you've got to show here, that when n is greater than t plus s, see, this is all we've got to show. Okay, when n is greater than t plus s, we will show that Cn is 0. Okay, intuitively we've got the idea, but now we've got to actually give a proof for it. So when n is greater than t plus s, what can we say? Notice here that when I is greater than t, ai's will be 0, right? When I, see, we want to show that this is 0, right? Cn is 0. So one way of showing that Cn is 0 is to show that all these terms are 0, right? Each of these terms are 0. One thing we can definitely say is that when I is greater than t, then ai will be 0, because what is t? T is the maximum of all the n's such that an's are non-zero. That means after t everything will be 0. Okay, so when I is greater than t, this will always be 0. We have to just check for t is less than I is less than t. Okay, so if ai is 0, that means bi into ai will be, sorry, ai times bn minus I will be 0. Okay, now you tell me what to do. Okay, for if I is greater than t, please write in your own words. I stick to the way I like to write, so you can try writing in your own words. So if I is greater than t, what happens? ai is equal to 0, which means that ai times bn minus I will also be 0. Okay, and if I is, now we need to check which case, when I is less than or equal to t, right? We would expect that if I is less than or equal to t, then the bn minus I is 0, right? We would expect that. Okay, I is less than or equal to t. In fact, see, so here I runs from 0 to n, so I have taken the cases when I is greater than t. So I would want just this part, when I, is it okay? I have taken the case, see, your I goes from 0 to n, right? When I is greater than t, we know all those terms are 0. We only need to check for less than t. That is when I is lies between 0 and t. Okay, so in this case what happens? You look at the n minus I. Where will n minus I be? What happens to n minus I? Can anyone see? Yeah? See, you can see this. You can see here that t is less than n minus s, right? So if t is less than n minus s, then what we will have here, so what we'll have here is I will be less than or equal to t, which is less than, strictly less than n minus s, right? What does this tell us? Which implies that n minus I is strictly greater than s. Isn't this what we want? If n minus I is greater than s, then what does this mean about bn minus I? It will be, what is s? The stage at the last index for which bn is non-zero. That means bigger than that, everything will be 0. So that means bn minus I will be 0, which means that ai times bn minus I is 0, and therefore for any n greater than t plus s, Cn, which is equal to summation I going from 0 to n ai bn minus I is 0, because each of these terms are 0. I hope everyone has got it. I have taken this in two parts, less than t and greater than t. When it is less than t, first I take greater than t. Once it's greater than t, all the ai's are 0, and if it is less than t, then all the bn minus i's are 0. It's quite simple. You can check. So therefore, what do we have? We have proved that ax into bx is in the set, that is Rx. So therefore, a of x into b of x is in Rx, and hence Rx is a subring of Rx. Okay, so it's a ring on its own with the type of multiplication that we have used and type of addition that we have used in this. That is, you remember how we had defined multiplication and addition? Use that same multiplication and addition here. It is a subring. Okay, that's all that we needed to prove in this. Now we can pull off the results. Okay, but there is something interesting that happens here. You have a special index here, that is the, in this there is a special index, that is this S and T, right, the degrees. Okay, that's what we need to know, something little more about the degrees of the polynomials. So for that, I'll give you some terminology which we will use later. I would suggest that you all try to prove these things on your own if you like, because if you manage to do it on your own, you will definitely be able to reproduce it. So let's see one. Just the definition is, okay, so this set which we have defined in the above exercise, so if R is a ring, then the set which we have defined in the above exercise in this manner, Rx equals whatever it is, that is after some stage all terms are 0, is called as the polynomial ring, called as the set of polynomials over R. Okay, and the elements of this are called what? What are the elements of this called? Polynomials. Okay, and the elements of Rx are called so that's what we think. We will use this terminology in this manner itself. So, of course, the set embedded with those two operations, the plus and dot of the formal power series, are the operations. With that we have a ring, right, the polynomial ring. I hope that's clear. And some terminology. So keep in mind what we have proved here. There is one very important fact that we have proved here, right? There is one important fact that we have proved here, that is, when n is greater than the sum of the degrees, I will be defining the degree now, but notice here that in this section I have proved that when n is greater than the sum of the degrees, then all the Cn's are 0, which essentially tells us what it tells us about the degree of a of x into b of x. It is exactly, it tells us that it is less than or equal to the degree of a of x plus the degree of b of x. It does not tell us that it is equal to the degree of a of x plus the degree of b of x. It tells us that it is less than or equal to the degree of a of x plus the degree of b of x. I hope everyone can see that, because this says that the maximum value should be less than or equal to t plus s. Okay, I don't know that the t plus s value is non-zero. The t plus s value might also be 0, okay, and it can take place. We will see some cases where it takes place in some rings. Okay, in nice rings we expected it does not take place, but it takes place in the bad rings. Okay, so some terminology. One is we want to know what's the degree of a polynomial, right? So that's, so if again this is all there on your notes. So if this is a polynomial, okay, that means after some stage this is all 0, then we define the degree, then we define the degree of a of x to b, okay, which we will write as degree of a of x. What is this? It's nothing but the maximum value of all the n in n union 0. There is one thing that I need to mention here, n union 0, such that so there is a one case in which this is not defined. Can anyone tell me? The maximum of all n in n union 0 such that a n is non-zero. There is one case which we will not be able to define this. Which one? What 0? 0 polynomial? If you have the 0 polynomial, what happens? All the ans are 0. I mean, this set is empty. What is maximum of the empty set? Can't talk about it, right? So it's not defined. So we want to see that this is non-zero when we define the we want to see that this is the non-zero polynomial when we define the degree. Okay, so we will only define the degree for non-zero polynomials. Okay, the 0 polynomial we do not define the degree. So we do not define the degree for the 0 polynomial. Okay. What is the degree of a constant polynomial? Constant polynomial means the 0th term, so you have the 0th term and after that everything is 0, right? That's the constant polynomial and not the constant sequence. The constant sequence is not a polynomial because it will never be, you will never be able to find a largest element, I mean largest index to it, right? Because it's always not the constant sequence. Okay, it is the constant term, that's what we call it as, right? So what is the degree of the constant polynomial? 0. Okay, 0 polynomial we do not define the degree. Non-zero constant polynomial it's 0. Otherwise 0 polynomial we do not define the degree. Please remember that. This if the degree is m, if the degree of the polynomial is m, okay, then we call so the coefficient, right, corresponding to the highest corresponding to the degree. Okay, so this is called as the leading coefficient of Ax. Okay, this is all terminology you are familiar with. Okay, we call Am as the leading coefficient of A of x. Okay, purposely putting down these notation, this terminology, because I will be using it in proofs. So I will not redefine all of these things. So this is called as the leading coefficient. Please understand what it means more than trying to memorize. Does anyone know if the leading coefficient is 1, what do we say call the polynomial as? Monic polynomial, right? If the coefficient is 1, if the leading coefficient is 1, okay, that's another terminology, not writing. You can, so if the leading coefficient of the polynomial is 1, we call it the polynomial as a monic polynomial. That's the, and a polynomial of degree 0 is called as a constant polynomial. Okay, that's the basic terminology which I will be using in the proofs. Again, there's a small remark here coming from this theorem itself, from this part. What is it? The remark is okay, so if A of x and B of x are in Rx, let me just write it like this, remove the 0 polynomial. In fact, I'll stop writing 0x and just write 0 now. Okay. Then degree of A of x times B of x, okay, is less than or equal to, let me in fact put down another remark also, less than or equal to the degree of A of x plus the degree of B of x. To do this, you simply have to imitate the previous proof. To prove this, you just need to imitate this part of the previous proof. Okay, your t is nothing but the degree of A, your s is nothing but the degree of B. Okay, t is nothing but the degree of A of x, s is nothing but the degree of B of x. That's what we had taken t and s to be. Okay, so that's the reason I purposely did it in that manner. Secondly, I would like someone to tell me what is, can you give me an upper bound for the degree of A of x plus B of x? Okay, because I don't want to write it. What is it? The maximum of the degrees. Okay, you can, of course, you can say sum also. That's also an upper bound, but it's not as good. This is the kind of the least upper bound, because we will definitely be able to find polynomials where the degree of A of x plus B of x is exactly equal to the maximum of the degrees of A of x and B. For example, you just take B to be 0 is less than or equal to the maximum of the degrees of A of x. Then in fact I'll put 1, 2. We have, again, if you want to prove this, imitate what we have done for A of x minus B of x. Exactly the same thing works, right? Exactly the same thing what you prove for A of x minus B of x is going to work here also, right? I hope everyone can see that. Okay, so now is the interesting part. We are like looking to see, we all know that polynomials are nice in real analysis, but can I do some work in algebra with it? Okay, so This is a small one. I'm not even going to prove it for you. So if, by the way, this is another notation which I generally fix. Whenever I want to talk about an integral domain, I will generally use D. Okay. And when I want to talk about a field, I will generally use F and K. Standard kind of notations. E, F, K kind of. Fields would be most likely E, F and K. Integral domains, I generally use D. Okay, so if D is an integral domain, I dot D means integral domain, then dx is an integral domain. Okay, how do I prove this? I know that if D is an integral domain, then then this ring of formal power series over D is also an integral domain, right? So there are a few things that you need to prove. One is you need to show that this is, so what do I need to show? Commutative ring, unity element, right? No zero divisors. Is it commutative? Definitely. We have proved that if D is commutative, then the formal power series is commutative. Any subring of a commutative ring is commutative, right? So this is going to be commutative. Does this have the unity element? You check and see. If 1 is the unity here, what will be the unity here? The constant polynomial with leading coefficient 1, right? That is, the 0th coefficient will be 1 and then 0, 0, 0, 0. That will be your unity. And that is going to be in this, right? Because eventually all terms are 0. So that's a polynomial. Can everyone see that? Okay. So that's the, that means this is commutative ring with unity. And third, I need to say that it has no zero divisors. Why it has no zero divisors? Suppose it had a zero divisor, say A of x, that would mean that there is some non-zero element. So that if it had a zero divisor, that means you would be able to find non-zero elements A of x and B of x in dx such that A of x into B of x is 0. But this A of x and B of x are also in this, right? So this would mean that this also has a zero divisor. So that's a contradiction because this is an integral domain. Okay, so simply using the fact that this is an integral domain, I can show that this is an integral domain. So that's the way I'm going about it. I'm not doing the proof twice. So you can write that out. It's just a 2-line proof. Okay. And so I hope this is something interesting to you. This gives us some examples, some interesting facts. It tells us that the polynomials, look at the polynomials over Z, that's going to be an integral domain, right? The polynomials over Z is an integral domain. The polynomials over Q is an integral domain. The polynomials over R is an integral domain. Q and R are all integral domains, right? So the polynomials, the ring of polynomials over Q, over R, over C, okay, are all integral domains. What about Zns? What about Zns? Not a. Can you tell me for which n's it is an integral domain and for which ones it is not an integral domain? Okay. So we know from this itself that if n is equal to p, means if n is a prime, then Znx is going to be an integral domain. What if n is not a prime? Then can you definitely say it's not an integral domain? What zero divisors will you see? If n is not a prime, can you for sure say that Znx is not an integral domain? What zero divisor will you see? The same ones which are in Zn. Look at the same ones, look at the corresponding constant polynomials, right? Which are the ones which we had taken in Zn? If n is not a prime, that means there are some non-trivial divisors, right? There's a non-trivial divisor d and its corresponding n by d, the complementary divisor, right? So d is non-zero, n by d is non-zero, but d times n by d is n, which modulo n is 0. Okay, so d times n by d in Zn is 0. So 0, d is a this thing, 0 divisor. Look at the corresponding constant polynomials, that is, take the 0th term to be d, everything else you take as 0. Okay, take the other one to be n by d, everything else you take as 0. When you multiply to these two polynomials, what do you get? You are multiplying, the multiplication which you are going to do with the coefficients are going to be modulo n multiplications. Even the additions are going to be modulo n additions. Think about it. What is this thing that you're going to get? Ask yourself, when you take the product of two constant polynomials, what is the maximum possible degree you can expect? The maximum. What is the maximum of 0 and 0? 0. So the degree of the product will be maximum this thing. So you just need to check, yeah. Sum. Thank you. So the degree of the product will be maximum, will be at most the sum of the two degrees. Okay, but again the sum of the two degrees is 0 only. So maximum you can expect it to be there. And what is the 0th coefficient of the product? It will be, what is the 0th coefficient of the product? Look at, you can look at, take d to be a non-trivial divisor of n, right? This is a non-trivial divisor. Take a of x. What is my a of x? It is going to be, let's use the notation which we had used last time. You can look at something like summation d times delta 0 comma n x raised to n. I don't know if you are comfortable with this. What does this mean? This delta 0 comma n will be 0 when n is not equal to 0. Right? That means d times it also is going to be 0. And of course here again I am going to do modulo n multiplication, even though it's not required. And just the first term is going to be d. So d, the 0th coefficient is going to be d, and then 0 0 0 0. Okay, take b of x to be summation n by d. I hope everyone can see that n by d is going to be a natural number because d divides n. So n by d is going to be a natural number. This times, right? Actually, when we write generally when we write like polynomials over R, we simply denote this by d itself. We do not distinguish between the constant polynomial and the constant in notation, and that's a good reason for not doing that. We will see later. So what happens to a of x into b of x? We know that the degree of this cannot exceed 0, so we don't have to worry about terms after the 0th term, right? The degree of this cannot exceed 0, so we don't have to worry about terms after the 0th term. So we only need to check the 0th term. What is the 0th term? What is the 0th term? It is going to be the 0th term of this into the 0th term of this, but modulo n multiplication. So what is d times n by d? Modulo n multiplication will give us 0. So you are going to get 0 times x raised to n, which is nothing but, so this is a non-zero polynomial, this is a non-zero polynomial. When you take the product, you get a 0 polynomial, so it is going to be it's not going to be this thing. This also gives us another, okay, that is not this thing, let us keep that out. So what we have proved is that, in fact we have proved something a little more than this. We have in fact proved that when R is not an integral domain, Rx is also not an integral domain. That's essentially what we have proved. Look at the corresponding constant polynomials. Okay, when R is not an integral domain, So R is an integral domain if and only if Rx is an integral domain. Or yes, in fact we have proved something a little more than that also. We have proved that R has no zero divisors if and only if Rx has no zero divisors. Anyway, so that's that. So I don't write out these basic proofs, okay? Takes up a lot of time. Yeah, so the next big interesting question for us is, we know that when we multiply in general, rings when we multiply two polynomials, right? When we add, we don't know what to expect, right? We don't know what to expect the degree. Only thing we can say about the degree, even in the rings which we work in normally, like R, C, Q, whatever, we don't have any expectation for the degree of A plus B. We only know that the degree of A plus B is at most the maximum of the 2 degrees, right? Because what happens is, if you have the nth term here and the nth term here, if they are additive inverses of each other, then they will make 0 when you add up. So we cannot expect, we don't have any expectation. I hope everyone has understood what I said. If the nth term here is the additive inverse of the nth term in the other polynomial, when we add, that term is going to become 0. So we have no expectation for the degree of A plus B. It's quite natural. But we do have an expectation for the degree of A into B, right? Whenever we multiply in R, C, Q, N, okay, it always seems that we get the degree of A into B as the degree of A plus the degree of B, right? So a nice question should pop up. It should ask you, like, which are those rings in which this actually takes place? Okay, can you give me the set of all these rings in which this takes place? And it turns out that it becomes the, anyone knows? Integral domains. Okay, when D is an integral domain, we will want to show that the degree of A into B is actually equal to the degree of A plus the degree of B. Okay, I hope everyone is okay with that. Before we do that, maybe we will look at, maybe let's see if someone can give me examples of, can anyone give me examples of polynomials in say Z6, such that the examples of polynomials in Z6 such that the degree of A into B is not equal to the degree of A plus the degree of B. Yeah? 2x cube. Okay, so you're just taking these two polynomials, right? Okay, 2x cube, when we say this, let us start understanding what these polynomials are. The coefficient of the x cube term is 0 and the coefficient of every other term is, sorry, the coefficient of the x cube term is 2, coefficient of everything else is 0, into what you said, 3x square. But I'll tell you why I don't like this example too much, because the end one actually has no degree. Okay, so that's what we'll do, plus 1 plus 1. So that means the coefficient of x square term is 3, the coefficient of the x term is 0, coefficient of the constant term is 1. Okay, and what is this going to add up to? What is this going to multiply and give us? We know that the degree of the maximum degree we can expect for is the degree of x raised to 5. And what is the degree of x raised to 5? You have to take the element here of the cube element, multiply it to, you have to take all those possible, right? So it should be, if these are your an's, if this is summation an x, I'm just showing you how the definition is fine, otherwise you can simply multiply n, you would get what you want. But what would this be? This would be summation I going from 0 to 5 ai b 5 minus I, right? That's what this would be. But we know that the ai's only exist when I is 3. So the only one which is here is a3 b2, right? a3 b2 would be 6, or not 6 because we need to go modulo 6, so we get 0. So you saw what she has done. The fourth one would again be 0, you can check for yourself, and I will not really work this out. I will tell you that this is 2 times x cube. Okay, so what does this give us? 2 times x cube, and degree of this is 3, degree of this is 2, but the degree of this is 3, right? How did she get this kind of a example? By checking that, yeah. How? Yeah, you take this in such a way that when you take the product you get 0. Okay, so that's the way in which she has got it. So you can in fact see this does not ever work when D is not an integral domain. If it has a 0 divisor, then you will always be able to find some 2 polynomials for which you can get this problem. Okay, it was exactly the same way in which we got the other example. So what is interesting is this: if D is an integral domain, then for any a of x, let me write this as summation a n x raised to n, and b of x, which I will write as summation b n x raised to n in dx. Okay, difference, let me not include the 0 polynomial. That means a of x and b of x are not the 0 polynomials. The degree of a of x times b of x will always be the degree of a of x plus the degree of b of x. And how do we prove this? So to prove this, what I will do is I will simply show the inequality on both sides. This is less than or equal to this, this is less than or equal to this. Okay, we already know one side, right? For any ring we know that this is less than or equal to that, so that is already done. Okay, so we know the degree of a of x times b of x is less than or equal to the degree of a of x this I will call as 1. I want to prove the other side. Ask yourself, what does it mean to prove the other side? What does it mean to prove the other side? If I want to prove the other side, what does it mean? What do you mean by saying that the degree of a of x plus b of x is greater than or equal to the degree of a of x plus the degree of b of x? If I show that the coefficient corresponding to the degree of a of x plus the degree of b of x is non-zero, that means that maximum value, right, would have to be greater than or equal to that. If I show, so let's say that the degree of a of x is t and the degree of b of x is s. Let's call this as some Cn x raised to n. Okay, this polynomial we will call as Cn x raised to n. If I show that C t plus s is non-zero, right? What is the degree defined to be? The degree of this will be the maximum of n. such that Cn is non-zero. If I show that Ct plus S is non-zero, that means the maximum value has to be greater than or equal to T plus S. So that will prove it. All I need to do is show that Ct plus S is non-zero. That will prove my result. Okay. So let's see. So it's very simple. So let Ax times Bx be equal to summation Cn x raised to n. And therefore, what will happen to Ct plus S? Ct plus S, what is this? This is summation I going from 0 to T plus S, Ai B T plus S minus I. You might get confused with notations if you are not sure of it, but go back and think why. You will get comfortable with it. The more times you go back and ask yourself why, you will get comfortable with this. Okay. So what is this fellow here? Ask yourself, in polynomials, when I multiply polynomials, right, I want to first see, whenever you try to do a proof, first try to intuitively try to get what you are trying to work with, okay, at least on things which you are familiar with. If you take a polynomial of degree 5 and a polynomial of degree 6 and multiply it, right, in R, if you take a polynomial of degree 5 and degree 6 and multiply it, what is the coefficient of the x raised to 11 term? The product of the two highest coefficients, right? Because that's the only way you can get x raised to 11 is by taking this 5 and that 6 and multiplying it, right? So here also, what do you expect this to be? What do you expect this to be? Later on we'll prove it. First, what do you expect? Yeah? At Bs. Everyone can see that? Highest coefficient here is At and highest coefficient here is Bs. So you expect it to be At into Bs. Okay? So that means let's show that everything else is 0. Will be done. Okay? If we show that this is At Bs, our proof is done. Why? Because the degree of this, where is it? Oh, I have not written here. I have not written this. Let the degree of a of x be t and the degree of b of x be s. Okay, we know that they are non-zero polynomials. Degree of a of x is t will mean that at is non-zero, right? That's the maximum value which is non-zero. After that, everything is 0. Okay, the degree of this is s will mean that bs is non-zero. So I know that at and bs are non-zero. They both come from the integral domain, which means that their product should be non-zero, right? Because they come from the integral domain. So if I can prove that this is at bs, I'm done. So prove that everything else is 0. Okay. So to do that, what do I need to do? Notice here, when I is equal to t, what is the term that you will get? At bs, right? When I is equal to t, what do you get? At b t plus s minus t, which is bs. Okay, so when I is t. So when I is not equal to t, prove that this is always 0. So we know this similar type of computation earlier. We have done the same computation. So for I greater than t, okay, for I greater than t, we also wanted to be less than this thing. It's okay. For I greater than t, less than or equal to t plus s, what happens? Ai will be equal to 0. Hope everyone agrees with this, because the degree of this is t. That means after this everything is 0. Okay. Hence ai times b t plus s minus I would be 0. Right? This is 0, so this has to be 0. 0 times something is always 0, right? And for So this is when I is greater than t. I have to check when it's less than t. Don't check for t because that t you don't want it to be 0. Okay. The tth term is non-zero. We know in fact that the tth term is non-zero. Don't check when you know that. So when I is less than or equal to I, strictly less than t, what happens in this case? We know we cannot say anything about ai here, so there is no other option but to check what happens to t plus s minus I. Okay, so you tell me what happens to t plus s minus I. What will happen to t plus s minus I? What do you need to show? You need to show that t plus s minus I is greater than, you want to show that this product is 0, right? You want to show that this fellow is 0. When will you be able to say that it's 0? If t plus s minus I is greater than s. So you need to show that t plus s minus I is greater than s. How will you show that? You know that t is greater than I. So what will happen to t plus s minus I? T plus s minus I will be greater than, t is greater than I plus s minus I, t is greater than I, right? So this will be, so you are essentially just adding s plus I on both sides, so this will be s. So that means t plus s minus I is greater than s, which means that very simply b t plus s minus I is 0, which means that ai times b t plus s minus I is 0, and therefore what we have proved is that c t plus s, notice why I don't write these things out, I am telling you, we have shown that when I is less than t, here these terms are 0, when I is greater than t, these terms are all 0, so the only term left out is I equals to tth term, only the tth term is left, so that is at bs, which is non-zero. So therefore ct plus s is non-zero, which means that, as I have said earlier, this means the degree of a of x times b of x has to be greater than or equal to, why? Because this is the maximum of the non-zero terms, right? Maximum of the subscripts of the non-zero terms. It's maximum of n, so that Cn is non-zero, right? And this is non-zero, so therefore the maximum value has to be bigger than it. So therefore this is greater than or equal to t plus s. This t and s are nothing but the degree of a of x and the degree of p of x. Combine 1 and 2 and you have got your result. Okay. Yeah. So what is the time? Yeah, I will take a short 5-minute break.